Hello. Well, first, let me introduce ourselves. This is José Antonio Sánchez. He's
Hi.
a senior data scientist in Trilogic. And my name is Roberto Díaz. I'm the head of the data science research line in the same company. And this talk is about a project we had with El Canal de Isabel II that, in our opinion, is quite interesting because it combines Internet of Things, deep learning, and it's a project that is already in use. So let's start with the motivation. When a city grows up and we need to include more water supplies, if we need to bring water from a different water source. This implies higher cost, environmental damage, and poor quality. And as I said here, the largest, less expensive, and most environmentally sound source of water is the water currently being wasted in every sector of our economy. To make use of and improve our efficiency, we need good demand management policies. To understand of our demand, the residential use of water compose the 70% of the total water consumption. A good understanding of this consumption and their internal details will improve our management policies. We can make use of many different artificial intelligence techniques to understand this problem. For a perfect understanding of the demand, we will need to use a device, a meter in every device. Imagine a meter in every tap, in every washing machine, in every toilet. This is extremely intrusive and also very expensive. To overcome this problem, it's possible to install a unique water meter in the main connection, and there we can include many different predictive models. A predictive model to predict the end use of the water flow, if it's a washing machine, a tap, a shower. We also can include forecasting models to predict future demand. The data source for this project, well, Canal de Isabel II, since 2008, is monitoring a set of 300 homes. In these years, they have collected more than 15 million hours of water consumption. So this is a big data set. This group of 300 homes is quite representative of all the population in the community of Madrid. And their goal is to study and address different data science problems. This is the title of the project, Pattern Recognition in Residential End Uses of Water. And in the project, there were two companies involved, Exceleria, in charge of the pre-processing task, and our company, Trilogic, in the machine learning and artificial intelligence task. Our company is an SMI company that is involved in many research programs, like the European Horizon 2020 program. We cooperate with many universities, and our goal is to transfer all this knowledge in products and services for our customers. Now, José Antonio will introduce the preprocessing.
Right. Now I would like to show how the data is created. Here we can see a picture with infrastructure, hardware infrastructure. We have one water meter installed on each house, just one water meter. It can be of 1 liter of precision or 1 deciliter of precision. This means that once 1 liter is consumed or 1 deciliter is consumed, the water meter emits a pulse. It is connected to a data logger that records the time when the pulse was emitted. It is equipped with a GSM modem, and it sends the data to the control center in a daily basis. Okay, once we have the data in the control center, this data is labeled by operators who are experts and use, with the help of specialized software, label the events. This task is a tough task. It involves a considerable amount of time. For instance, in order to analyze just a two-week period of data from just one installation, it takes about an hour. So it's clear that an automatic system is needed to label the events. These are the types of events that we are taking into consideration. We have faucets, cisterns, showers, including bathtubs, washing machine, dishwasher, pool, irrigation, and also leaks. Okay, and now we're going to see a previous analysis and visualization. Here we got the baseline information is what we received. We received the date and the number of accumulated pools. Well, we took this data and we said, okay, let's represent it and let's see how we can start from here. And what we can extract from here is nothing. We can see here a bunch of lines and we don't know what to do with them. So the goal now is to convert the pulse to flow. This means convert the discrete signal to a continuous signal so that we can see how the water is being consumed, when the flow grows, when the flow is declining, and see the shape of the flow. Okay. And here we got a first approximation. Here we are supposing that we got a water meter of 1 liter of precision, and we also are supposing that once a pulse was emitted, the last 10 seconds there was a continuous flow of 1 deciliter. This was just the first approximation. The final version we used moving averages of different order. And once we have the flow, if we added the information of the events, the labels, we can see we can see a lot of information. We can see what are the habits of the tenant. For instance, this is Monday. We can see that someone at 1:30 more or less used the toilet. Then we can see they have shower at 8:15, and so on. Here we got an example of a Sunday at 5:15. Someone uses the toilet, so maybe someone arrived home after partying or not. Then there is at 9:30 there is another action, and also the Sunday evening seems to be a good time to do laundry, especially if you have been partying and sweating and dancing all the night. Okay. And well, gossiping people can have a good time seeing this kind of things. Now we're going to see what's an episode. It's easy. An episode is a period of time where the flow is distinct to zero, and it's between two zero flow instant. An episode may consist of one or more events. For instance, if I am using the shower and someone at the same time is turning on the faucet, are two events and form an episode. And an event only belongs to an episode. Okay, an event is an elementary unit of consumption that occurs in a period of time of enough duration in which the instant flow can be clearly differentiated from the rest. A particular domestic use may consist of one or more events. For instance, the events related to appliances like a washing machine or dishwasher that have several filling cycles. Each one of these filling cycles is considered a different event. And one or several events that converge in time form an episode. Well, this is what we are saying now. Here we got an example to see 3 domestic uses which involve 4 events. Here we got the first washing machine cycle is an independent event. It coincides in time with the faucet. Then we have the cistern and the second cycle of the washing machine. Well, these 3 domestic uses involve 4 events and 3 episodes. The first episode is composed by the 2 events that coincide in time, that are the faucet and the first cycle on the washing machine. The next one, the second episode is the cistern, and the third one, the washing machine. The second cycle of the washing machine. Well, let's summarize now what we did. First, we convert the pulse to flow by means of moving averages, 2 moving averages, and then we need to simplify the flow and convert, make the flow look like a geometric shape, like, I don't know if it's the correct word, or a trapezoidal shape. And this is achieved by means of another moving average. Okay, and now we have to identify the different events. When an episode consists of more than one event, the events are overlaid. Okay, we saw now how this was, and graphically the events are stacked on others as a ladder. And how do we discriminate events? Well, we are talking about the same event when the flow keeps constant or the change is insignificant, okay? Or is a different event if there is a significant change of the flow. Here we got an example of, this is an episode composed of 2 events, shower and the faucet. This one is composed by 3 events. Okay, now.
Well, the approach. Here you can see a full picture of all the preprocessing. On the top, you have the pulses. Then we evaluate the flow, and it's divided in 3 different events. After that, we extracted 37 features from every event. Here you can find some examples: duration, volume, maximum flow, the initial gradient, the final gradient. And we made use of deep neural networks to classify the events. Why neural networks? They are very powerful techniques, And some years ago, it was a field that was strictly academic. But now we can make use of many different frameworks like TensorFlow, CNTK, Keras, Big Deal. At the end, we have many different tools. All of them require a lot of expert knowledge. It's complex to fine-tune every detail in a neural network. And they also require a lot of training data. In our case, with 15 million hours, it was more than enough. Their main problem is the training time. It's extremely complex. They require specialized hardware like GPUs, and they are also slow classifiers. Our main problem was that they require a solution with no need of GPUs. And we were thinking about how to speed up the training procedure. I'm sure most of you are familiar with neural network, are layers of neurons organized by lawyers. The training procedure is called backpropagation. The algorithm can train very fast layers that are near the output, but it's a procedure that is slow with neurons that are far away from the output. For this reason, in other domains, in different domains like image classification, a lot of people make use of pre-trained neural networks. Images, as you can easily find, classifiers for images. When you train a classifier, the neurons at the beginning learn genetic features that are useful for every problem. The neurons at the end are specialized in features that are specific for your problem. For this reason, when you use a pre-trained neural network, you already have at the beginning useful features, so the training procedure is very fast. We cannot find a pre-trained neural network in this domain because it's extremely specific. We make use of a different techniques called stack denoising autoencoders. It's a technique to pre-train a neural network. It's fast, and you can make use of unlabeled data because it's an unsupervised technique. A denoise autoencoder the idea is very simple. It's a neural network with just one hidden layer where you put in the input your data with noise, and at the end, you want to recover the original input. If you choose a very reduced number of neurons in the hidden layer, you learn features helpful to compress the information. And if you choose a high number of neurons in the hidden layer, then you learn alternative complementary features to solve the problem. The technique, stack denoising autoencoders, is very simple. It's just train different autoencoders sequentially, and it's based on using the same weights to pre-initialize at the end your neural network. We can see here how is the speed up. With autoencoders in just 20 epochs, we have the same result that in 80 epochs when you didn't use anything, when you learn from the scratch with random values in your weights. Here you can find an example of the results. We benchmarked, we made a benchmark with a very common algorithm, support vector machines that are nonlinear. And in the case of deep neural networks with 1 liter meters, we reach an accuracy of 81%. In the case of super vector machine, it's extremely low, 67%. was the best we can do with them. In the case of 0.1 liters meters, are more precise, are meters that are better. We reached 91%. We had 8 different classes in the neural network. And in the case of super vector machines, only 84%. Here you can see in the case of 1 liter meters, the most complex one, the error by the different end uses. Super vector machines perform extremely bad, and they confuse a lot of washing machine with dishwasher, for example. And neural networks achieve higher accuracy in every kind of water consumption.
Okay, now we would like to tell you what else can deep learning do for water supply companies. Water supply companies are at least interested on two kind of use cases where deep learning can be the solution, or maybe deep learning can achieve good results. One of them is water demand forecasting in order to improve or optimize the system operations, plan for future purchases of water, plan for future revenues and expenditures. And the other one is the weather or quantitative precipitation forecast, or even alert systems in order to take the appropriate steps to reduce the damage caused by storms, natural disasters, etc., and limit the risks for infrastructure, people, and goods. These kind of problems are presented as time series, and the problem is time series forecasting. We have a kind of neural networks that works very well with this kind of data. And well, traditional neural networks assume that the samples that compose the inputs are independent of each other. This assumption is not valid with time series, because well, the recurrent neural networks receives as input a sequence of or a sequence as input, and use the information of the past to predict the next step. Okay. These recurrent neural networks incorporate a certain kind of memory that contains the sense of what has happened previously. We have the LSTM, that are long short-term memory, that is a variant of recurrent neural networks that are capable of learning long-term dependencies. The internal architecture is more complex than a simple recurrent neural networks architecture, and is the most wide used of type of recurrent neural network. Now, we would like to show you a very, very simple example. This is a public data set that is the Southwestern Precipitation Forecast. It contains the monthly precipitation in liters per square meter of this on the Southwestern mountain region between 1932 and 1966. Okay, this is a very small data set, just 420 rows and 2 columns, the month and the precipitation. Here we got the data displayed. And well, with a very simple architecture, very, very simple, this is not deep learning, it's just one hidden layer, with the input sequence of each 12 time step in just one feature and a hidden layer of 20 LSTM, we achieve quite good results of the model is grown in just 17 liters per square meter in average, okay, on each prediction. These are quite good results, and just with one hidden layer, but suppose that we can add more information, more features. For instance, in this kind of problem, we can add information about temperature, wind speeds, etc. And we have a large data set, and we can add more lawyers, more dropout lawyers, etc. And we can achieve a very good and accurate result. Well, here we got how was the prediction of the last 15% of the data, the last 73 months. In blue color, we can see the test data, and in orange, the prediction. And we can see more or less are it takes how is the time series, but it can be improved if we had more data, and etc. This was just an example to express the potential of LSTM with time series. And now some conclusions.
Just to finish the conclusions, data science can help us to understand all the water demand and its characterization. Deep learning models can achieve very good results in terms of accuracy when you have a very large training set. It could be very useful to create, with this knowledge, good management policies. And this methodology is actually in use for processing a panel of many homes in the community of Madrid. Yeah, just to finish, thank you everyone. And if you want to know more information, we have a stand outside, so we can solve any question or what we can talk about.
And if you want more information about this project, you can go to the web page of Canal Isabel II, and you can download, I think it's Cuadernos I+D Canal, something like that.
And you can
the number 25 is the Cuaderno number 25.
Yeah.
Thank you.